Alrighty then. Thank you all for coming to join this session. My name is Joe Wagner, and I'm with the Energy Trust of Oregon. And today we're going to be joined by Mike Cairns and Bryan Uhler to talk about Windows, a key ingredient to a comfortable home. With that, I'll let you all take it away.
Test, test.
Hello.
Thank you, Benji. Thank you. Well, thanks everybody for coming. Today we're going to talk about Windows. The main theme of this whole event is really comfort. So tonight we're definitely, well, this afternoon, feels like tonight for him because he just got in from Europe just a couple of days ago. But we want to make the connection between fenestrations, holes in our building envelope, and the occupant or the people. We want to make sure that people are healthy. When you look at the slides, there's going to be some of the slides that have a lot of technical jargon. Don't worry about taking pictures of those things. You'll be able to get access to the slideshow later. So if you write technical specs or things like that, or some of this stuff easily goes over our heads, you'll have that as a resource later. So just some of the shopkeeping there, housekeeping. Tell you a quick little bit about myself, and then Mike will talk about himself. I'm a second-generation builder. My dad started the company in 1978. We still work together, although he's pretty well turned it over to me. In fact, our electrician was just communicating with me, and my dad and my mom are going to go out to the job site either today or tomorrow to try to help when it comes to some placement there. So we work together. I've got hands-on experience, but there's been a huge transition in being more of a technical builder in the last couple of decades. For us, it started out with structural engineering and shear. So when I see buildings like this, I think about that. But now we're getting far more technical on the energy side. So hopefully there's some practical application that we can help you with. And then I'll let Mike explain himself, especially, and he's kind of a second-generation window guy, his background.
Thanks, Bryan. Like you said, second-generation window guy. And like Mark was saying earlier, you know, once you're in the construction industry, you're in it. It's the same with Windows. Sometimes I feel like Al Pacino. You know, it's like, every time I think I'm out, they pull me back in. When you're in Windows, you're in it forever. And I think one of the reasons for that is because, you know, in the Pacific Northwest here, we went through the leaky condo crisis, and we learned a lot about the potentials for failure in buildings. And it really showed us how critical the windows are to, you know, structure, comfort, durability. And, you know, it actually kind of shows just how important the fenestration is at the end of the day. And that appeals to me. And the more I learn about building science, the more it reinforces that concept. So without any further ado, let's get into the thing. So I have a little quote here from Mark Twain. I think this is particularly apt. It ain't what you don't know that gets you in trouble. It's what you know for sure that just ain't so.
And maybe I'll comment on that a little bit. When it comes to the window side, I have known in our projects, most of ours are spec homes. We've built a lot of pre-sales, a lot of customs. I have known that our windows were our weakest link in our building envelope design. My background is finance and accounting, so I still do our cost accounting, our payroll, and it is really hard to know how much high-performance windows cost and to be able to get that at the sale. Because if you can't, how do you justify putting those types of things in? And not everything is a $2.5 million custom project. So I'm trying to approach it, and I'm still trying to figure it out, how to do things that are as good as possible while still being economically feasible. So as we look at our history of fenestrations a little bit, maybe somebody can just throw out, what do you think these openings in the castle are for? What are some things that would have been good for the occupant, for the people? Ventilation, going to the bathroom. What was the last one? Lighting? Yes, very good. How about keeping the horde from entering the castle. So those could be like arrow slits, balustraria if you want to look up the word. So it was more for preventing egress, people coming in and attacking your family, than some of the other building science things. We don't have to deal with that so much unless you're Josh Salinger living in Portland. But just kidding, Portlanders, just kidding. But we can see how things have changed throughout the years, and Mike did just come back from Europe, so he's going to show you a little bit more of the history of openings in our walls, really.
Yeah, there's obviously, as a couple of people highlighted, ventilation was one of those critical aspects. The only way to heat a building back in the day was burning wood inside, which creates a tremendous amount of smoke, makes it very unpleasant inside, so they needed to get fresh air. And obviously letting in some light, which is hard to come by. This was a really cool window that I came across in a castle there. I'm just going to press play. So this is how they controlled the opening. So they've basically got like a log inside there, and they can turn it. So they can direct the wind flow, direct their view. I wouldn't say overly spectacular performance, but I guess better than just a raw opening. Oh, there we go. Now, here are a couple others. So you can see on the far right, this is a window intended to allow light in. And you can tell that it's a window that's only there really for light because of the shape of the opening. They're like, oh, we got these tremendously thick walls, but if we just have a straight cutout, it's not going to give you the light inside. Like the center window, that one's there for ventilation. It's just a cut through a 15-foot long or wide wall. This one on the far left, that's down in a cellar or a basement, and they've just got this tiny little window way up high. And that's actually a really interesting concept because it allows them to ventilate the smoke from up high, but it will allow some cool air to run down low for ventilation purposes. It obviously wasn't providing them with a heck of a lot of light. So they kind of, because of the technology at the time, they had to sort of pick and choose. What is this window going to do? Is it going to ventilate? Is it going to provide light?
Maybe I can ask you, Mike, tell us about Empress Elizabeth. I thought that was a pretty interesting, what they had to do for her comfort. We're going to talk a little bit about what is a comfortable home here.
Yeah, in the palace in Innsbruck, that was a living space for the Habsburg royalty. And when the Empress Elizabeth was coming to town, they would start getting ready 3 or 4 days ahead of time because she had a specific temperature. She's like, it works out to, I think, 18.4 degrees Celsius. But it has to be exactly this temperature. And so then they had to use drapes and curtains and tapestries on the walls, and they had to have fires in some areas and windows open in other areas so that all of the royal suite was at exactly the right temperature. And it takes this gigantic team of people to maintain that temperature when you don't have effective wall assemblies and fenestration.
So that's kind of what we do in design and construction, is we're not building for Empress Elizabeth, so to speak, but we want the house to be comfortable. I don't know if it's been talked about too much in our presentation so far, but here's a definition that was given. Comfort is often defined as a state free from distress, a lack of negative stimulus. It's also a sense of contentment, security, ease, and of well-being. So there are a number of sensory sensors on our bodies that contribute to whether or not we feel comfortable or not. As we look at our picture here, we can see this person who is clearly in distress, whether he realizes it consciously or not. Subconsciously, his body is, because he's too hot. So thermally, we can feel too hot, we can feel too cold, and oftentimes it's the difference in temperature from our bodies, what it wants to be at, versus mean radiant temperature or what the temperatures of the surfaces around us are. We're going to talk more about how energy can flow, but sensory comfort was the main point there.
Yeah, and in homes and buildings, Obviously, there's a couple other things that we would want to consider, including physical comfort, like space design, accessibility, and psychological comfort, feeling secure from forced entry, reducing climate anxiety, that sort of thing. Now, honestly, we can pretty easily design a building that's going to perform very, very well. It's basically a concrete bunker with a bunch of insulation. It might have one door in it. That thing is going to be secure. It's going to be comfortable. It's going to be highly durable. It's going to be a horrible place to live. We need to have a connection to the outdoor. We need that mental connection. We need to see the outdoors. We need to feel and smell fresh air on a regular basis. We need to be able to get out of that building if there's a fire or some other threat of some kind. So we have to take that perfect assembly, smash a hole into it, and then fill that hole with something that allows us to still control those different aspects. We want ventilation when we want it. We want light when we want it. So we have to use a window to control those things. So we're talking about sunlight, ventilation, protection from hot and cold, protection from loud noises, and security from, whether it's just bugs, animals, people, whatever. I guess one other thing is, are the windows that we're currently installing in homes actually accomplishing all of those tasks? In my opinion, most of the time, the answer is no. They aren't spectacular at controlling all of those different aspects of comfort. So we'll just dive a little bit deeper into how we're failing our buildings and ourselves.
So the first thing we'll talk about is natural light, but before that, just again to give you a little bit of background, when you look at this building that we're in right now, it's fairly easy to trace the structural loads. It's a pretty honest building, and if you've been in construction for any period of time, when you see these different framed elements, your eye picks it up quickly. You can see your posts. I'm pretty sure that this hardware was not the original hardware, probably retrofit as you look around. But you can see the plate metal, the bolts, the steel that's involved, the car decking, the purlins. When you've been a framer, it makes sense. It's a language that you speak. You can talk to each other even if you've never met before and have those conversations. My experience with Windows has been totally like a different language. These are a couple of cross-sections of Windows. The first time I had seen a cross-section, it was like, didn't even know what I was looking at. And so part of the intent of this talk here is, yes, it'll have some of the deeper things, but it's to become more familiar with the language so that when you see a cross-section, your eye can stop and understand what it is that you're looking at. I remember the first time they went over a window schedule. This was like 20 years ago, and it was just like over my head. So hopefully this will help a little bit. So when it comes to the natural light, obviously the most energy efficient, thermally transferred building would be one with no openings. But when you look in here, how much artificial light do we have? There's just a couple of them, but this is a very well illuminated place. We put windows in our walls in order to get light. People tend to want large windows. Well, the way the code is heading is toward having triple glazing. That means 3 panes of glass. You're putting another third of the weight just with the insulated glazing unit. That's what an IGU is. So you have to start thinking when it comes to the creation of a window frame, does it have the structural capability of carrying its load and then transferring it through its structural system? So you have to be thinking about those types of things.
Yeah, and the hardware as well. And one of the other considerations is how we ventilate a room. How would we naturally ventilate a space? Oftentimes the answer would be, well, we'll open a window. But is it really that easy? Have you ever opened a window and been disappointed? I'm going to introduce everyone to Bob and his cat here. So Bob and his cat live in a fairly typical apartment in a fairly typical building. This is a very common window design. It has been for decades, where you have a large window with a small operable awning sash down near the floor. So Bob's getting hot, wants to cool down his home. He has to bend over, try to crank open that little awning sash. Bending it down and cranking the handle is kind of annoying, but it's going to be so great when he opens that window. Unfortunately, a look at the science behind air movement may disagree with that concept. So the sun shines, heats up that facade. That hot air wants to move upwards. That's the way it works. And those awning sashes actually become a fantastic redirector or funnel to force that warm air inside the building. And on the inside of the space, warm air is also rising. So what happens is, basically from the top of that window opening and up, the air continues to get warmer. You pile up this hot air pressure. Whatever cool air is in there will be forced out the window. The cat is totally happy. Nice and fine, might be cool enough to lay in the sun. Bob's dying. Also, when we do large windows, how do we try to protect from other concerns than just the heat? So this is pretty typical up in Canada. Everybody's got lots of hockey sticks, and when you break the end off the hockey stick, what do you do with it? You cut it down and use it to stop your sliding window from opening. That's a Canadian security device. So you can do that on a sliding window, door, vertical slider. It works great, but maybe there could be a better way. Has anyone ever lived in a house where the room with the nice big windows isn't that usable in the summer because it's just too damn hot? Or conversely, in the wintertime, do you need to wear a parka when you're sitting down to dinner in the dining room or something like that? My grandparents' house basically had a summer side and a winter side. In the summertime, you stayed on the north side of the house, and in the wintertime, you stayed on the south side of the house. That was just how it worked.
So the question is, what if? What if there's a better way? In our company, we've done the same typical window designs for, I would say, decades. You know, I've been working intimately in the company for probably 25-ish years without too much of a change in how we've done our windows. So what if you could be in your dining room and be perfectly comfortable? Or to speak to Mike's point, especially if we're doing more multifamily buildings and we're getting these large elevations, our windows perform the way that we wanted them to perform. Or instead of Mike's hockey stick analogy with his security, even the hardware. This is a holistic approach to window design and construction. The hardware allowing us to feel safe and secure inside our buildings, not easy to open up. All right. This is two of us doing this, and we've not done this before, so bear with us a little bit here.
Yeah, we've got the
All right, sounds good.
the sense of thermal comfort in the space. Now, this one here is a really interesting one to look at because your comfort is actually based on heat loss. We're endothermic creatures. We produce heat. So comfort is a factor of how quickly you lose that heat. So there's 4 different things that will affect that. It's going to be, there's minor internal storage, there's some evaporation loss, radiant exchange with surroundings, and loss by convection. That means it's affected by humidity levels, surface temperature, air temperature, and convection. Air temperature is only one part of how you actually feel the temperature and how comfort occurs. Thermostat is a terrible indicator because it's actually only telling you 3 of those 4. It's 1/4 of the formula. So level of activity, recent conditions, personal preferences also affect that. But there are 3 types of heat or cold transfer. Ooh, I pressed the wrong button.
And maybe I'll just touch base on one of these points just a little bit more, talking about the thermostat versus the humidity. If you remember the slide that Mike showed, the higher in elevation the building gets, if you have an opening window, you're inadvertently directing that air into your building. So you might be adding a latent load, meaning more humidity. And being down here in Portland, I'm up from across the water from Seattle, Kitsap Peninsula. It's not as humid as it gets down here in the summertime. So if you're adding that latent load into your house or into your building, you also may be influencing your mechanical systems. So I think, again, being kind of a bean counter by trade, there's also the security of cost. So could you have smaller cooling and heating equipment, depending on what you've done for your windows? If you're not introducing the outdoor air, especially depending on what your deltas are, could your operational costs be lower? So think about those factors too. Don't make these decisions in a vacuum, but a very holistic support or approach, structure, your windows, all of those things together.
So now let's try to dig a little bit into the nuts and bolts about how the windows specifically affect that thermal comfort. When it comes to comfort, oftentimes it starts at the design. A home made entirely of glass probably isn't going to be very comfortable. As we said already, a home made with no glass is not going to be comfortable. So trying to find that balance between your opaque wall and your transparent wall assemblies is one of those keys. When we look at windows, oftentimes making your windows larger is actually the best way to go. Not the largest possible windows is the best solution, but the larger you make the window, the better your glass to frame ratio is going to be, and it's going to improve your thermal values. The fewer openings that you have in your building, instead of having a bunch of small windows, you have one large opening. Simplifies things for a bunch of different reasons. Makes your framing simpler. It lowers the thermal bridging from your frames, from your installation transitions. It makes your waterproofing a heck of a lot easier. Your finishing carpenters will definitely appreciate fewer windows to trim out. There's less drywall. Like, it snowballs and has this massive effect where you make everybody feel better inside the building, and at the same time, it's less expensive and easier to build. So it's really a huge win-win when you're talking about that stuff. So the number and size of your operable windows, that will have an effect. These windows here, for example, probably would have been about the same price to have one single large operator. It would have been slightly more expensive, but you get a much larger operator. You actually move your ventilation up higher in the building so that it's more effective because the pressure is higher as you go up higher, so the higher the opening is, the better it works. So that would have been a nice change to make. I mean, they probably did this for the aesthetic and trying to replicate the original view, but in terms of pure functionality, you would let in more light, you have more view, that sort of thing. Yeah?
Are the triangle and trapezoid windows up at the top, are those unusually expensive and difficult?
They're a little bit more expensive to make than a rectangular window, but it's not a crazy change, it's just a slightly different shape.
So like it's your bullet points about keep window design simple.
Yes.
Avoid those if you can handle the architectural compromise.
Absolutely. So, there's always a very valid argument to make between aesthetics and functionality. So the pragmatic approach would be to keep all of the windows rectangular. That's definitely going to be more optimal in terms of budget, design, ease of build. However, this building definitely has a very impressive aesthetic as a result of those rake windows up top. So, yeah, it's an excellent point for sure. Definitely something to keep in mind. Grids are one that, to me, are actually a little bit of a pet peeve. I am not a huge fan of grids. They lower your performance. They make it harder to clean the windows. I think they're kind of a pain in the butt all around, and they detract from your light, your view, everything. I feel like imprisoned when I have grids all over the windows. That's obviously just personal opinion, but I think it's a good way to go, to just have larger spans of glass.
Maybe just a couple of other things. If you're doing architectural design or you're doing load calculations for heating and cooling equipment, how many windows there are on the wall and what that ratio is in the room makes a difference. So when you've got an outside corner like this, it is a different window to wall ratio because two of these walls, if this was the room here, now have openings to the outside, and they can be facing different directions, right? South, west, make sure I've got my cardinal directions right, versus east or north. All of those have an impact on comfort, especially depending on the time of the year that you're at. So you might specify your windows a little bit differently depending on the room that you're in and even what the need of the room is.
For sure. A window or door is essentially a gigantic hole in the wall. And, if we're going to fill that hole in the wall with a window or door to control the movement of air, it should probably be effective at controlling that movement of air. Putting in a leaky window is, I don't think, a particularly great solution to the problem. So looking at air tightness, I personally am a huge fan of the passive house concept. I built one myself and live in it. And it really is like, you take a bunch of the best practices and put them together in a system. And it works out pretty nicely. And they actually look at it and say, okay, well, facade components, to be able to meet your target, should have a maximum air leakage rate. And 0.05 CFM per square foot is that leakage rate. And that's actually very similar to, as you can see here, the NAF's infiltration exfiltration A3 or C3 rating. No, that's wrong. It's A3. So that's the maximum air tightness level that NAF's. Holy cow, that was bright. So
that's artificial lighting.
Yeah.
That is not natural light, in case you're wondering.
So, if your window is at that just barely meeting that A3 rating, it's actually just barely appropriate as a facade element if you're looking at a high performance standard like passive house. So you definitely want to go for something a little bit better than that, in my opinion.
And a little bit more on the air tightness. Again, trying not to think of any of this in a vacuum. No pun intended. I'm sorry, I'm a dad, I had to say it. If you're trying to get lower blower door numbers, your windows is a part of that equation. So you can pay attention to the interface of your sheathing, to your mud sill, to your concrete, if you're doing monopoly framing, things like that. But the windows that we've done in the past had that little kind of fuzzy gasket. You're only going to be able to get so airtight because of that. So yes, what Mike's talking about is what they test the windows at, but it impacts the whole. One of the questions that came in, which was nice in the app, had to do with sliding glass doors. It's almost impossible to get, a white vinyl sliding glass door airtight. There's that runner at the bottom that just leaks air like a sieve. So I was with one gentleman, and he was doing blower door work, aero barrier, not the local aero barrier, I won't call out who it was, and he wanted to tape the opening. Well, that's going to change your blower door number. That's not how the house is performing. So I believe in passive house you have to do a positive and a negative pressure, and you average them.
That's correct, yeah.
So if you're doing that, you want to make sure that your windows are part of what will allow you to meet that level of air tightness. Ultimately, this talk is about comfort, but it is nice to know, even on the code side, how you can make sure you pass them. And I'm doing a natural experiment right now. One house, very builder basic windows. And next door to it are these high-performance triple pane windows. They've got multiple gaskets, which is part of that air tightness story. And now I'll get to see, not just theoretical, what the blower door score comes in differently. So that's something I wanted to mention on the air tightness side of things.
Call it a case study example. So on my house, first house my dad and I have ever built, obviously we've been in construction for a while, but we had never built a house before. So it was our first kick at the can, and our blower door was 0.18 ACH 50. So I think that was pretty good. I can't help but think some of it is due to the fact that the windows and doors are actually very well performing. If they had leaked, there's no way I could have achieved that kind of a score. So these slides are a little bit detailed in terms of what it's really digging into. We've got, U factors, and one of the things to keep in mind is traditionally, a lot of the measurement for windows was actually glass only. And there are still some manufacturers that give glass only numbers, but that's missing a big part of the picture. You can lose a ton of heat through the frames. And that would have a huge effect on the comfort of the occupants as well as the overall thermal model for the building. So we definitely have to keep in mind that we've got framing material and insulation. There are some other things that affect the thermal performance, and that includes the depth of the IGU, the number of glass panes, the thickness of the glass panes, and the type and location of low-E coatings. UF is what the passive house system would use to describe the specific frame component.
The text afterward, it's like saying glass and frame. Can you go back to last slide?
Yes, UW would be glass and frame, correct. Correct. What have there was some animation I didn't know about. So this one has a whole bunch of information. What I think is probably a bigger deal to take away from here is the difference between R value and U values. Personally, I'm a huge fan of U values. Most of the window industry already uses U values and has for a very long time, and there's a good reason for it. So R value is resistance to heat transfer. U value is an actual measurement of the heat that's transferred. So that gives you something that's quantifiable. It's not just like, this is how strong our block is. This is how much heat gets through. So you can quantify those losses for the building, and it makes your energy model very accurate as a result. And there's lots of things that will go into it when it comes to the windows. You can see in the real world examples up on the table there that you can affect it through a few different methods. If we take a look here, we can actually see that there's a few different ways that we have thermal losses.
So we tend to be very heating dominated with the conversation, but a lot of the Earth's population is not British Columbia, Seattle, Portland. So it's not just heat loss in the wintertime, but the same principles apply when it comes to heat gain in other parts of the United States or other parts of the world. If you take a look here, there's a couple of different examples of what we can see. So just a quick run through. When you look in the center here, you can see the steel for the reinforcement. I'm assuming it's steel. Yes. Not iron. Over here, there's some composites. This is kind of that light green. Those different components are required for the structure. We build in a high seismic design category. If you build more on the water, you might have more wind loading. So you have to pay attention to the structure, but can we build in such a way to limit that thermal transfer? And when you look in here, it looks kind of like a honeycomb. Remember, it's not the insulation unless it's a thermal mass. It's not the insulation that's providing the thermal resistance. It's the stillness of the air pockets within them. So when you look at something like this and you can see that there's a lot more small pockets, it's going to perform better. There's also quite a few little seals. We can open it up, show you later. These are stainless steel spacers, right?
Correct.
And if you think about how electricity flows, you use copper wiring, right? Because the electrons are going to be able to flow easily through there. You're not using wood when it comes to having your electrons flow. So just think about something similar when it comes to your spacers. Different spacers allow more heat to conduct one way or the other. In this case, there's a composite one. Then to fill up some of the cavity here, we have an insulation. We have some aerogel in here. All of those components lead to allowing less thermal transfer of energy. That's like the high level what we want to remember, is the way we build and design our windows can have a direct effect on how easy energy can transfer through.
Exactly. And then the one thing that's sort of missing and is often kind of forgotten when it comes to, call it like building codes and a lot of modeling, is they'll forget about the fact that you have to install it in an opening. So you'll look at your, like your NFRC U values, and you say, oh, well, that's from the edge to edge on the frame. And then your building model has a value for the wall, and then there's this half-inch gap between the wall and the window. And it's just kind of like, well, you know, we'll throw that away and forget about that. It's no big deal. But we've actually seen some buildings where the real model, when they calculate that installation value, it can have such a massive impact. There's one multifamily building in North Van where they were able to reduce from 10 inches of insulation on the outside to 6 by changing that installation detail. So that's a huge, huge potential for loss. The FRSI is kind of a complicated thing at the end of the day. What you sort of need to know about that is it's really about surface temperatures. And that's a big deal when it comes to not just your building model, but the comfort of the occupants. Because you will feel that radiant temperature difference if you have objects in the space that are cooler than the average of, or cooler or warmer than the average of everything else. You feel a radiant transfer. That's that thing where if you're sitting by a cold window in the wintertime, it's not drafty, but it's just sucking the heat out of you. It's kind of like if you're sitting around a campfire. You're like the front, you're getting the radiant heat transfer from the fire, so you're blistering hot on the front, and then your back is freezing. Like, how is that possible? Why can't I get some sort of temperature balance? And it's because of the radiant difference. And you can get that inside of a building if you have surfaces that are lower or higher temperature. And what you also get, if temperatures are too low, you have a risk of condensation, which is a huge risk for building security. It's a big risk for occupant health. One thing that a lot of people don't realize is that generally the higher performance the building, the higher your humidity level will get until you're around 50%. That should actually be your goal humidity. A lot of very poor performing windows are kind of predicated on a model where you have a furnace blasting, drying out the inside of your home. Maybe you're on the prairies, and when it gets cold, it also gets ridiculously dry. But they will only function at low temperatures if the humidity levels are below 20%. So if you are in a high performance building and you're in an area like here where we have very high average relative humidity levels, it's moist all the time, we have a long drying cycle, those poor performing windows are going to be very problematic for the security of the building and for the health of the occupants.
So we'll talk a little bit about our IGUs. We've covered some of this already. Excuse me. So paying attention to the different spacing in between your panes of glass is important. There's a size of space that if there was only 2 of these panes, you would want. But it's easy if a manufacturer already is making double pane windows to try to squeeze in a third pane of glass. So you want to have the proper distance between these, but you don't want to be so wide that you start getting convective looping within your windows. So I haven't done the math on it, but here's what we're saying. Ideal is 1 inch for dual pane, 1.5 inch for triple pane. So that's important to know when it comes to specifying. And then, of course, we talked about the type and quality of spacer. The thickness of glass is going to be important. And then the type of gas that's in there. So argon or krypton. It's taking all my self-control not to make a Superman joke about being a Kryptonian or something. But anyway,
Totally.
we get the idea.
We're getting buzzed on time, so we'll see if we can do this faster. So
He means I'm talking too much.
yeah, you're the one. So the low E coatings, they're how we deal with the radiant temperature differences. And the important thing to keep in mind is that there is an inherent balance between heat that you will retain, heat that will come in, and heat that will be lost. So if you're shooting for high solar heat gain, you are going to get less well-performing U values, because if you're letting the heat in, that also means you're letting the heat out. So it's kind of a fine line in that balance, how you build out your model. So if you have something like a low E180 coating from Cardinal, it'll let in a fair bit of solar heat. And my hair's gray now, but I used to be a ginger, and I would get sunburnt through low E180. So it's not my favorite coating, but it works for a high-performance model. And if you keep the shading in mind, it's a fantastic way to make your thermal model work. Generally, we tend to see something more towards this type of value. Solar heat in the mid-30s tends to be a pretty good all-around option. But there are some higher insulating or solar heat gain resistant coatings down below 0.3, and that would be ideal in like hot climates. Shading's an important thing, especially if you are going to use higher solar heat gain glass. You definitely need to use some kind of shading to prevent the solar heat gain from coming in when it's undesirable. And there's a couple of different ways that can be done.
So as we see here, we've got some trees that provide a lot of different things. You can add architectural elements as far as shading. It's kind of the gift that keeps on giving. So thinking about those things at the design phase, look at your site that you're building on. What's its orientation? What views are you trying to keep track of? Active versus passive, all of those things should come into consideration.
I have a couple examples here from Europe of some passive shading solutions. One fairly modern, the other one obviously not as modern. Both of them, you can see those shade lines on there, just how effective they are in late afternoon sun. And actually the older model, to me, appears to be a lot more effective. Larger glass letting in more light, but very effective shading. There are also active shading solutions like this one. This one's kind of neat. It's a solar-powered screen solution, mounts directly to the window frame, and you can see from the inside, in the center, that's actually what it looks like when it's down, so you can still see through it fairly well, but from the exterior, it's very opaque. It's over 80% solar rejection, so super effective. And natural ventilation. So if you have, oftentimes as you get into higher performance, windows that are very high performing are often tilt turns. And that tilt ventilation takes advantage of the natural stack ventilation. The larger opening is higher towards the top. And what's great is you get the Venturi effect. So obviously, the stack effect means that you're going to have the warmer air up top. It's going to force its way out the top of the window. But it has to be replaced with the same volume of air. So that air, the opening is decreasing as it comes down, so that volume of air is coming through the bottom that's decreasing in size, and it's the Venturi effect. So the same as with plumbing. If you have the volume being squeezed through a smaller opening, it increases in velocity. So that's actually going to propagate a natural convection, ventilate without having to have a second opening. You can allow the physics of the inside of the space to control ventilation. You don't have to worry about exterior wind direction or anything like that. It simplifies the ventilation concept quite a bit.
Then we talk a little bit about acoustical comfort. There's a big difference in sound. You know, if you're ever with a really nice high-performance vehicle and the door closes and it just sounds like it's got a good, hefty seal, it's the same thing that can happen with windows. By paying attention to the materials, and if you're increasing the mass as well as things that don't transfer sound so much, you have a quieter home. And you can definitely feel that in terms of occupant comfort. It goes full circle, not only the materials that you're building with, the number of panes of glass and all of that, but the air sealing side. So sound waves are going to transmit much easier through an open room like this than if it's partitioned up and it has things that will collect and hold the sound. So there's another part of that.
Yeah. Call it one of the last things here is the physical and psychological comfort. So it's kind of an amorphous concept, but it's something that I think is really interesting. There have been some studies recently that have shown that rates of mental illness and people's general senses of unease and discomfort in general increase as you decrease the amount of green space. People get trapped in this concrete jungle, this urban environment, and they need a connection to the outdoors. They need a connection to green space. We're very fortunate in our part of the world that we tend to have a lot of greenery around, but if you're just stuck inside of a building with no windows, you don't really get that connection for a good portion of the day. So it's important to make sure that you have a lot of openings so that, you know, no matter where somebody is in a building, you can get that mental connection to the green space outside.
Yeah, and that was kind of the big, as Mike used the word amorphous, it's difficult to quantify. Some of these other things you can use metrics that are scientific in nature, but even having financial stability can lead to psychological well-being, to have your house feel solid. If you're in a high seismic design category or Miami-Dade, if you're building in a place that feels secure, there's an effect that it has on our minds.
Another interesting one is there's been a few studies that were done that showed that when people feel that they have, like as soon as you have a sense of control over your surroundings, you actually feel more comfortable in those surroundings. So when you have the ability to go and open a window and ventilate, even if it's not actually changing the temperature, the fact that you have control over it will actually make you feel more comfortable in that environment. And it's a really interesting phenomenon, that control over it, the thermostat, the windows, whatever it is that causes or should be causing comfort. It's great to make that as accessible as possible to everybody.
So we've got just our key takeaways. Comfortable home is an airtight home. Think about the window holistically. All of the components that make it up impact its ultimate performance. You don't have a Ferrari with lousy wheels. Everything is designed and integrated together in order to have a high-performing automobile. Same thing with our windows, and expanding that, our entire home. From the structural systems, the mechanical systems, the plumbing systems, that to me is how you get to a truly high-performance building.
So, do we have time for questions? We're all out.
Yeah.
But both of us are still here, so if anybody does have any questions, feel free to come and harangue us, whether we're over there or over here. I welcome any questions, obviously. I enjoy talking, so.
Thank you guys so much.